In the three-dimensional world that we live in, we encounter many different kinds of solids. Some are regular, some are irregular. But there's a particular class which is generated by rotating a curve or an area about some axis. Examples are spheres, ellipsoids, toroids, cones, etc. In this lecture, we're going to see how to calculate their surface area and then their volume. I'm going to begin with the notion of integration as area under a curve and as a summation. Let's look at this little area that's before you. The length in the x direction is dx. So dx, which is a small length, is not to be understood as d multiplied by x. Instead, it's to be understood as this small length delta x, as delta x becomes very, very small. The height is y, and so the small amount of area is dA, which is y dx. Now, of course, if I had a curve, so this is the y direction over here, and the height of each of these is y, and as x changes, y changes. Y in this case is f of x. In that case, the total area A would be the summation of the little areas dAs. So the little areas, which is y dx plus y dx plus y dx and so forth. So this area plus this area plus this all the way up till the end. As dx or delta x becomes smaller and smaller, this then becomes the integral from this point here, A, to this point here, B, of y dx. Or you could write it as f of x dx. But this is stuff that you already know. What we're interested in this lecture is to calculate the surface area that is generated by rotating this curve f of x. Rotation means that we're going to take the x-axis and rotate the curve around this, in which case we shall get a figure that looks like this. Concentrate your attention upon this little strip over here, and to see this even more clearly, let's look at this red strip here. If you were to open out this red strip, then you would get this strip flattened out. It has got radius 2 pi y. That's because this is a circle of radius y. It has got length dl, and hence the small amount of surface area would be dA, which then is 2 pi y dl. In order to understand dl a little bit better, I'm going to draw a little triangle like this. If we move a distance dx, that dx being the same as the dx over here, then we move up a distance dy, and dl is then this length here. So by Pythagoras' theorem, this is 2 pi y, and then dl is square root of dx squared plus dy squared. If I'm taking x to be the independent variable, then let me take dx out from the square root. So then this becomes dx square root of 1 plus dy by dx squared. And if I want the total surface area, well, I just add up all the little bits of area, and then this becomes the integral of what's over here. So that's 2 pi dx y square root of 1 plus the square of the derivative dy by dx squared. That is the area that is generated by rotating the curve y equals f of x. And the limit of integration goes from A up till B. So if we rotate this thing and look at the portion between A and B, that will be the surface area generated. We'll now apply the formula that we just derived, and here it is to remind you, to calculate a number of surface areas. We'll begin with the trivial application of an open cylinder. By open, I mean that we won't consider the end cap over here or the end cap on the other side. Just this shaded area is to be now found out. Let's put the origin of coordinates over here at x equal to 0. Take this length to be L. So this is the point x equal to L. Let's call this radius of the cylinder A. And so basically what we have to recognize is that this cylinder was generated by moving this flat horizontal line around the x-axis through 2 pi. So y as a function of x is trivial. Y is simply A. And so dy by dx is obviously 0. And hence the area of the cylinder is 2 pi integral dx going from x equal to 0 to x equal to L. Y is simply A. And what's in the square root is 1 plus 0. So that's just 1. Let's now integrate this out. And so there's only the integral of 1 from 0 to L, that's L itself. And that is the surface area of this open cylinder. Next, we'll use the same formula to calculate the surface area of an open cone. A cone, of course, is very familiar to us. We'll take the origin of coordinates at the vertex. So here x is equal to 0. And the height of the cone shall be taken to be h. So here is the point x equals h. Obviously, this cone has been generated by rotating this line, and the equation of this line we can easily get. It's just a over h x. You see that when x is equal to 0, y is equal to 0. When x is equal to h, y is equal to a. From here, dy by dx is a over h. And so what we need is the integral of y being just a over h, x. And then we have to have the square root of 1 plus a squared over h squared. And the integration is from 0 up till the maximum value of x, which is h. And now we can notice that this square root of 1 plus a squared over h squared is just a constant. We can take it outside. So this is 2 pi a over h into the square root of 1 plus a squared over h squared. And the integral is that over x, which goes from 0 to h. And now that's easily done. This is 2 pi a over h square root of h squared plus a squared. At the bottom there's h. And then when we integrate this, we get half h squared. So this h squared cancels over here. And what we get is then pi a into square root of h squared plus a squared. That's the surface area of this open cone. Now, of course, h squared plus a squared, that's this length. That is to say, from here all the way up till here. That's square root of h squared plus a squared. And so that's the length of the side of the cone. We're now going to get the surface area of a sphere using the same formula. And here, this sphere has been generated by taking this half circle which I'm trying to draw, which bounds this sphere, and rotating through 2 pi. Now let's get first of all the equation of the half circle. Well, the equation of a circle is x squared plus y squared equals a squared, where a is the radius of the circle. And just to remind you why that is so, let's take this circle, take a point on it. This point is x, y, which means that if we start from the origin and move a distance x over here, and then move a distance y here, then this distance is square root of x squared plus y squared, and that is the radius of the circle a, hence this equation. Now let's solve for y. Y becomes square root of a squared minus x squared, but then it could also be plus or minus. Actually, these are two different functions. You could say y1 is plus square root of a squared minus x squared, and y2 is minus square root of a squared minus x squared. That reflects the fact that there's a semicircle above and also that there is a semicircle below. But now let's come to using this formula. So obviously dy by dx, and I'm just going to take the positive root over here, dy by dx is then minus 2x over a squared minus x squared to the power half, and then there's a half here, so we just have dy by dx is minus x over that. In that case, the square root factor 1 plus dy by dx squared is 1 plus x squared over a squared minus x squared, and that is, obviously when I add these two together, is a over a squared minus x squared to the power half. So the area, or rather the surface area of this sphere is 2 pi dx, and x goes from minus a to plus a. Why is that? Well, let's look at this diagram over here. X starts from minus a, goes all the way up till plus a, and so that's reflected in the limits over here. Then we put in y. Y is a squared minus x squared to the half. And then we put in the square root. The square root is, or rather the square root factor, which is a squared minus x squared to the half. This and this cancel. So this is then just 2 pi a, and the integral of x from minus a to plus a, that's equal to 2a. So we get the familiar, well-known result that the surface area of a sphere is 4 pi a squared. And that's the right answer. Just one point that you need to remember. You could have taken the lower curve and rotated it through 2 pi. You would have gotten exactly the same answer. But you cannot take the whole circle and rotate it through 2 pi, because then you would get the sphere twice over. This problem is not going to be quite so easy as for a sphere. Here we've been asked to calculate the surface area of this watermelon, and this watermelon is mathematically close to being an ellipsoid. An ellipsoid is what we have over here, and it's obtained by taking an ellipse, which I'm trying to draw, or rather half an ellipse, and then rotating this ellipse through 2 pi along the x-axis. The equation of an ellipse is x squared over a squared plus y squared over b squared equals 1. Of course, if a and b are the same, then this is just a circle. Well, we can solve for y. Y is b into the square root of 1 minus x squared over a squared. And again, there are two roots of this, plus and minus. We're just going to take the plus and rotate that around to generate this ellipsoid. Now, the next thing, as we can see over here, we need to calculate this square root factor. So dy by dx from here is obviously b over a. And then here we have minus x divided by square root of a squared minus x squared. Now let's put this all into the formula. So a becomes 2 pi and the integral goes from minus a to plus a. You see that when x is equal to either plus or minus a, y is 0. So this point here is minus a and this point here is plus a. Okay, so now we shall just put in y, which is b into 1 minus x squared over a squared to the half. And then we need to put in the square root factor. That square root factor is 1 plus b squared over a squared into x squared over a squared minus x squared. Now take this 1 minus x squared over a squared factor inside, and this becomes then 2 pi b integral dx minus a to plus a as before. And inside, what we have then, just simplify this a little bit. This becomes 1 minus a squared minus b squared over a squared, and there's x squared over a squared. Now you see that if a and b were the same, then we wouldn't have this x squared factor here at all. And then our answer would then be simply 4 pi a squared. If that is to say, if a was equal to b, but it's not. In order to do this integral, let's first of all give another name to this a squared minus b squared over a squared factor. Call p as a squared minus b squared over a squared. And let's put x equal to, let's say, a times s. So this integral then simplifies a little bit. It becomes 4 pi b a, and now the integral goes from 0 to 1, and the integral is over s now, 0 to 1, and inside we have square root of 1 minus p s squared. Now what I've done over here is I've noticed that if x goes to minus x, nothing changes inside. So this integral is the integral of an even integrand. Instead of going from minus a to plus a, I could go 0 to a and multiply by 2. So this 2 pi b becomes 4. Finally, this integral, which is now simplified, can be either done by hand using the techniques that we've discussed, or you can just look it up. The answer is b over 2a plus, here is the inverse of the hyperbolic sign, a squared minus b squared over a squared, and divided by twice square root of 1 minus b squared over a squared. As a and b become closer to each other, does this go over into 4 pi a squared? I've checked, and the answer is yes. It does go over into 4 pi a squared, which is the surface area of a sphere, but it would be very useful if you expanded around a equal to b. Rotating the area between two curves can lead to some interesting new shapes. Here we have this purple area, which is rotated not around the x-axis, but around a line which is parallel to the x-axis and below it. That is to say, at y equal to minus 1. Let's now rotate it around and see what happens. You see that it is making a shape that looks like a pitcher. It's got a volume and it's got a surface area. Let's run it backwards, and you see we get back to where we started from. Before I leave the subject of surfaces, I want to emphasize the difference between open surfaces and closed surfaces. Actually, this is a very important point in advanced mathematics. Here is a surface that is open. So is this open, but this over here is closed. Now, let's ask ourselves, what is the difference between the open surface and the closed surface? Well, the open surface has a curve that goes all around it and which bounds the surface. Similarly, over here, there is a curve that goes all the way around, and this bounds the cylinder. On the other hand, there is no curve that bounds this sphere over here. Now, to make this point in another way, let's say that I have some maybe very complicated surface, and here is now a curve that bounds this surface. So I've shaded it a little bit over here. If I take the radius of this, go to 0, in other words, if I make this curve here smaller and smaller, then I will go from this open surface to this closed surface, which does not have any bounding curve. This is closed. Let us now move on to the concept of volume. We are familiar with the basic idea, of course. If you have an area A, and it doesn't really matter what shape it is, but if it is moved up through a distance dx in a perpendicular direction, then the small amount of volume that is generated by moving it up is A times dx, and we'll call that dv. As I said, the shape doesn't matter. It could be a circle or anything else, but if it is a circle, then the area A is pi r squared, and so dv will be pi r squared dx. Now let us look at the volume generated by rotating a curve. I mean this curve over here, of course. Let's now look at the volume that is generated by rotating it around the x-axis. So here's a little volume element. That's this part over here taken here. And this area on top is pi y squared, and hence the volume of this piece over here is dv, which is the area pi y squared, into the thickness, which is dx. If we want the total volume that is generated by rotating this curve, then it is simply the integral, which is pi integral y squared. And of course, the limits will go from where we start to where we finish, A to B. This is the formula that will help us get the volumes of different solids. The application to finding the volume of a cylinder is very trivial. All we need to know is that y is A, and so the volume V is pi integral dx A squared. If we put the origin of coordinates over here, so this is x equals 0, then we simply integrate from 0 up till L, and that of course is pi A squared into L. That's just the cross section into the length of the cylinder. Let's get the volume of this solid cone. Again, as before, y is a over h, x. So when x is equal to h, y is equal to a. A is the radius that you see over here of the cone. And so what we need then is just the integral v, which is pi integral dx y squared, which is a squared over h squared x squared. And the integration goes from here, which is x equals 0, all the way up till x equal to h. Let's move this out. So this is pi a squared over h squared. And when we integrate x squared, we get a third h cubed. And so we found that the volume of a cone is pi times the square of the radius times the height of the cone. That's the volume of the cone. Let's get the volume generated by rotating the curve y equals square root of x. That, of course, is this curve over here. When it's rotated around, you generate this volume. That volume is given by this. So let's simply put over here y squared equal to x. And if we start from x equals 0 and go up till x equals, let's say, L being over here, then this is half pi L squared. Next, let's get the volume of the sphere. As before, we shall take a semicircle, which is over here, and rotate it through 2 pi along the x-axis. We know that the equation of a circle is x squared plus y squared equals the radius squared, and hence y squared is a squared minus x squared. Now, that gives us for the volume, v is pi integral dx y squared, which is a squared minus x squared, and x goes from minus a to plus a. In other words, this point here is minus a, this point here is plus a. But let's slightly simplify and write this as 2 pi integral 0 to a dx a squared minus x squared. That's because the integral from minus a to 0 is the same as the integral from 0 to a. This is, of course, an even function. Well, now we can easily do the integral. This is 2 pi. And when we integrate a squared, we'll simply get a times a squared, which is a cubed. And from here, we shall get a third of a cubed. And that's 4 over 3 pi a cubed. That, of course, is the volume of a sphere. Next, let's get the volume of an ellipsoid. The ellipsoid is got by taking a half ellipse and rotating that about the x-axis. As you remember, the equation of an ellipse is x squared over a squared plus y squared over b squared equals 1. From this, we can solve for y squared, which is then b squared into 1 minus x squared over a squared. Our volume formula therefore gives us pi integral dx, and the integral runs from x equals minus a to x equals plus a. So we start from here, x equals minus a, end over here at plus a. And inside we have, of course, b squared into 1 minus x squared over a squared. So that now I will write as 2 pi b squared with the integral running only from 0 to plus a. I've again used the fact that this is an even function. And inside we have 1 minus x squared over a squared. Now that integral is quite trivial to do. That's 2 pi b squared. Inside we have a minus 1/3 a. That's because x squared gives 1/3 x squared upon integration. And so finally we get 4 pi b squared a over 3. Now if a and b were the same, then this would be a sphere, and we'd again get back to the formula for the volume of a sphere. Finally, we'll calculate the volume and surface area of a torus. A torus is a figure that looks like this. It's obviously three-dimensional. It's familiar to us from rings, donuts, rubber tires, etc. The best way to understand it is from a cutaway drawing like this. So look at this little circle here and move this circle around in this larger circle until it comes back to its original position. This circle has been moved with this radius vector, pushing it all around. Now let's take another perspective on this. So if I cut across it, then here is the small radius a, which means that this shaded area over here is pi a squared. This larger radius is what we shall call c. And now imagine that we were to cut it at one point and then straighten it out. In that case, we'd get a cylinder whose length would be 2 pi c, or its height would be 2 pi c, and the area of cross-section would be pi a squared. That's what's over here. So we can immediately get the volume of the torus. The volume of that torus is the volume of the cylinder up here. So that's 2 pi c times pi a squared, which is 2 pi squared a squared c. That's the volume of the torus. If you want the surface area, that's also very easy. Just open this out in a strip. You see that we have 2 pi c again, and this 2 pi a, that's the circumference of this circle here. So going around it like this will give you 2 pi a. Therefore, the area, the surface area, will be 2 pi c multiplied by 2 pi a, and that's 4 pi squared a into c. Now, of course, this was a very intuitive way of doing things. We could have equally well done this using the integration formulae that we had discussed earlier in this lecture. This lecture must be considered just as an introduction to 3 dimensions. When we do calculus in many dimensions, then we'll learn how to calculate volumes much better, and they will not have to be necessarily of solids which are generated by rotation. But that is for a later lecture.